Hello everybody. So in this video we're going to prove the second version of Hilbert's Nullstellensatz, which says the following. So we start with a polynomial ring in n variables over a field k, and I assume that my field k is algebraically closed. And also let me just set some notation. If alpha is an element in Kn, right? So if it's an element, if it's an n tuple with elements in K, so it lives in the affine n space. So I'm going to denote by m alpha this ideal, the ideal living inside the polynomial ring. So the theorem says that we have a map going from the affine n space to the set of maximal ideals of A, and the map is given by setting this alpha to m alpha, and the theorem says that this is in fact a bijection. So first of all, before we move on to the proof, we have to explain why this map H makes sense. So we need to explain why this m alpha is in fact a maximal ideal, right? And in fact, this is going to be our first lemma, which is, it makes almost exactly the same assumptions, and I'm keeping the same notation, but I don't really need to assume that my field K is algebraically closed for this, right? So we're just going to show that this ideal is maximal, which, well, we're going to do it by showing that if I divide my polynomial ring with this ideal, then I'm getting something that's, this is isomorphic with K, right? Okay, so what do? We consider this phi alpha, which is going to be the homomorphism going from the polynomial ring to K, and this is going to get an arbitrary element polynomial f, and it's going to map it to f of alpha, which is of course an element in K. Now it's pretty obvious that this map, well, first of all, it's a ring homomorphism, but it's also surjective, right? If I give you an element lambda in K, then we're just going to consider the constant polynomial lambda, and evaluating at alpha, it's not going to change anything, right? So now the claim is that, we will show that alpha which is by definition the polynomial ring, modulo m alpha, is in fact isomorphic to K, right? And this is, if we show this, then we're done, because K is a field, which means that this is a field, which means that the ideal is the ideal m alpha is maximal. Okay, so what's the claim now? So we claim that the kernel of phi alpha is in fact exactly equal to m alpha, right? This is m alpha. Okay, now if I give you, so this inclusion is pretty obvious, because if I give you an element living inside m alpha, so it's going to be an expression of the form a polynomial times this guy, blah blah blah, a polynomial times this guy, right? So if you evaluate this at alpha, at this n tuple, then of course you're going to get 0, right? So this implies that if every element of m alpha lives in the kernel of phi alpha, because if I evaluate alpha, I get 0, right? So this is pretty trivial. Now let's see the other inclusion. That's okay. So let's suppose that we have an element f living in the kernel of phi alpha, right? So by definition, this means that f of alpha is going to be equal to 0. So what I'm going to do now, in order to show that f is an element of m alpha, I'm going to consider f modulo m alpha, right? So if we have f modulo m alpha, then it's easy to see that this is exactly equal to f of alpha modulo m alpha, right? Because f is a polynomial is something living in the polynomial ring, right? So it's a polynomial in n variables. And if I consider it modulo this ideal, then every indeterminate xi is going to be replaced by alpha I. So eventually, what I have is f of alpha modulo m alpha. But by assumption, this is equal to 0, right? So of course, this implies that f lives inside M alpha, and this proves our claim, right? So by the first isomorphism theorem, we have that the polynomial ring modulo the kernel, which is M alpha, is isomorphic to the image of phi alpha. But now, as we already mentioned, phi alpha is surjective, right? So this is just K, which implies that that this is a field, which implies that M alpha is maximal, which is what we wanted. So this finishes the proof of the lemma, which wasn't that hard. And now we can move on to the proof of the main result of this video, which is it's this version of Nullstellensatz, right? So as we already proved, now this map makes sense. If I have an element living in alpha and n space and I consider this ideal, then this is in fact a maximal ideal, right? So the map makes sense, and it's also pretty obvious that it's also well defined. So in order to prove the bijection, we have to do two things. We have to prove surjectivity and injectivity. So let's start by proving that the map H is surjective. Okay, so let M be an arbitrary maximal ideal of alpha, of the polynomial ring. Okay, and of course this implies that if I divide by M, then I'm getting a field. This is a field. Okay. Now it's also but alpha modulo M is also I claim that it's a finitely generated K algebra. Right, so in order to see why this is a K algebra, what we have to do is find the ring homomorphism going from K to alpha modulo M. But this is trivial because alpha is the polynomial ring, right? So it's obvious that this guy is a K algebra, and in order to see why this is a finitely generated K algebra, it's also obvious that it's generated by the xi's modulo M. Right, every element in here can be written as a polynomial in the indeterminates xi modulo M. So it's true that alpha modulo M is a finitely generated K algebra. But now, if we use Hilbert's Nullstellensatz version 1 that we proved in our previous video, what we get is that alpha modulo M is algebraic over K. Right, so because in case you don't remember, the first version said that if I have a finitely generated K algebra that happens to be a field, then this K algebra is algebraic over the field K, right? So let's call this fact number 1, maybe. Okay, and now let's also notice that what we have is, well, there is this map psi going from K to alpha modulo M, right? Which is, I mean, it's the obvious map sending lambda to lambda modulo M, but this is a ring homomorphism, but these guys are fields, right? So this is a field homomorphism, which has to be, it necessarily has to be injective, right? So what we really have is a field extension. We have this field extension lying around here. Right. In reality, what we do is we identify K with the image of psi, right? So I'm going to use this somewhere in the next 5 minutes. Okay, but now let me remind you of the following fact, that we assume that K is algebraically closed. But this is equivalent to the following. K has no proper algebraic extensions, right? In case you don't remember this, if you just Google K algebraically closed field, then I think even the page in Wikipedia is going to be enough. It has a short proof of this implications, right? So we assume that K is algebraically closed, is an algebraically closed field, and this means that it doesn't have any proper algebraic extensions. But now we just saw by relation 1 that A modulo M is algebraic over K, right? So this is an algebraic extension. So these two fields have to be the same because it can be a proper algebraic extension, which means that the dimension of this guy as a K vector space has to be equal to 1. So we must have equality of these two fields. But as I already said, we don't really have K being a subset of A modulo M. What we really have is A modulo M, that is this guy over here. This is equal. Has to be equal to the image of the map psi, right? Which is by definition these are expressions of the form lambda modulo M, lambda running over K, right? So for every J in this set, we can find an element living in K such that, so since we have this equality of sets, we have that xj modulo m has to be equal to some lambda j modulo m, right? Which implies that xj minus lambda j has to be an element of m, which of course implies that this ideal over here has to be a subset of M, right? Since this is true for every J, we get this this inclusion over here. But now recall that M is an ideal of the polynomial ring, right? And since we assume that it's maximal, we can have equality here. By definition, maximal ideals cannot be the whole ring, right? But now we just proved, I mean, let's say, okay, let's assume that we had that this inclusion was proper, right? But we just saw in the previous lemma that this ideal is in fact maximal, right? So this thing cannot occur because this is maximal. So we must have that the polynomial ring, that this ideal is in fact equal to M. And this finishes the first step, because we just showed that if we consider that the n tuple lambda 1 lambda n, right, and we map it through H, then this is going to give us M, right? So we proved that there is, we proved that if I start with an arbitrary element in here, a maximal ideal, then I can find an n tuple in here such that the H of that tuple is going to be the ideal M, right? So this proves surjectivity, and maybe I want to now, so in order to prove, to finish the proof, we also have to prove that H is injective. Okay, so this is easier than injectivity is in this case easier than surjectivity. Okay, so let's assume, okay, so let alpha and A and B elements in the alpha in n space over K such that we have this equality, and let's call these ideals M, right? So if we write this a bit better, we have this equality. Right, so we have this equality of sets. So let I be an arbitrary number between 1 and n. And we notice the following. So if I consider bi minus alpha I, this is exactly equal with the following. So we get xi minus alpha I minus x alpha minus bi, right? Because the xi's cancel and we get bi minus alpha I. But now this is, this thing over here is obviously an element of M, right? because we have this equality, right? And we called both of these guys M. So this implies that bi minus alpha I. So M is by assumption a maximal ideal, which means that it cannot contain units. Because if an ideal contains a unit, then it has to be the whole ring. But since M is maximal, that cannot be the case. Which means that bi minus alpha I cannot live in the units of this polynomial ring. But this is just k without a zero, right? Which means that bi minus alpha I has to be 0, right? And since this is true for every I was arbitrary, we prove that A is equal to B, which of course proves that H is injective. So now this finishes the proof of the theorem, and before we stop this video, I would like also to make the following remark that okay, so we proved that H is a bijection, but it's true. I mean, there are some more things that there's one more thing that is true about H, and it turns out that H is also a homeomorphism of topological spaces, right? So what does that mean? So what we have to explain, in case you haven't heard it before, is that H is that if we look again at H, let me rewrite. Right, it turns out that these sets actually carry a topology, which in both cases it's called the Zariski topology, and what we can prove, it's not, I'm not really going to do it, but it's not that hard. What we prove is that images and pre-images of closed sets are again closed, right? So what we really show is that H is continuous with if we endow both of these guys with the Zariski topology, and we also show that the inverse of H is also continuous. So this is a homeomorphism of topological space, and this is the last remark I wanted to make before stopping here. And yeah, so thank you for watching, and I'll see you in the next video, where we're going to prove version number 3 of Hilbert's Nullstellensatz.